My Mac and I are having a real good time here. We're having so much fun. Counter it, but Macs are so intuitive. Yeah, I'll show you intuitive. Smack you upside your freaking head. Anyway, so I'll show you intuitive. God, and they think they're so cool too. They just piss me off. All right. Anyway, sorry. Reference this. I guess this ain't Mr. Rogers, is it? All right. Anyway, an inertial reference frame is one in which Newton's law of inertia is valid. All right. So all accelerating reference frames are non-inertial. Okay. So the Earth is a non-inertial reference frame, but we're going to treat it like an inertial reference frame for our problems here. Okay. Now this is what I was talking about earlier. That Aristotle, when he got before I got interrupted earlier. In fact, take the phone off the hook so it doesn't ring. So when Aristotle thought things wanted to stop because his view of the way the Earth worked, everything either he had to really push it or everything was stationary. That's because he's here on Earth. Where if he was on a space station, he'd see that everything is moving. Everything's just floating around, and you push it, and it goes forever until it bangs into something else. It's really kind of cool. But anyway, all right. So now we'll talk about Newton's second law. Okay, Newton's second law mathematically is now this is the one we deal with the most. It's written as the sum of the forces, where the Greek letter sigma denotes the vector sum. Okay, so the sum of the forces acting on an object, that gives you the net force. Sometimes if the net force is zero, the thing's not going to accelerate. If the net forces are greater than zero, the thing will accelerate. The object will. Now it's not the object, it's the forces acting on the object. That's the most important thing you can get out of this. All right, so Newton's second law, when a net external force is acting on an object of mass m, the acceleration that results is directly proportional to the net force and has a magnitude. In other words, right here, A is equal to the net force divided by this little, the inertia of the object. In other words, how much it does not want to move divided by how much it does not want to move actually gives us an acceleration. So we actually get this, then the sum of the forces is equal to the mass times the acceleration. He actually proved it as the sum of the forces is equal to, the net force is equal to the inertia of the object times the change in velocity or the change in distance. Okay, so that's where he got his acceleration. All right, F equals ma. It's huge. The units for it, kilograms, meters per second squared. It's a kilogram meter per second squared. It's called a Newton. Not a fig, but a Newton. Okay? All right. There's the SI units is the Newton. The CGS units for the grams is the dyne. Okay? All right? And the British Empire stuff is the pound. Pound and Newton are forces. Okay? Our mass in the British system is slugs. All right? So what does this look like? All right, so we draw a free body diagram of the forces. This diagram that represents the object and the forces that act on it. Okay? Okay? So the opposing force caused by this car, which it does not want to move. Okay? And there's forces there that are keeping it from rolling, from moving. I kind of wish they hadn't used a car because it's actually frictional forces on the tires that are moving that are working against it. But once we get a car moving, it's actually the frictional forces that. Okay, I'm not even going to get into it. Not now. It's too complicated. I wish they'd used a sled instead of a car because once you introduce wheels on the ground, the problem becomes very, very difficult. But for our purposes, it's okay. We'll just say, okay, well, the opposing force is 560. But they're pushing on it with a force of 275 plus 395. So what is the net force? The sum of the forces here in the x direction. The sum of the forces here in the x direction then is equal to 110 newtons. Let's say the mass of that car is 1,100 newtons. Okay? If the mass of the car is 1,100 newtons, then the acceleration of the car is 110 newtons divided by, or kilograms. Okay, let me show you. Getting tired. All right, so here we go. So we came up with that net force was equal to 110 newtons. All right? So what's the accelerate, which is equal to the mass of the car times the acceleration? Let's say the mass of the car, this is what I was trying to do, is 1,100 kilograms. Okay, the mass of the car is 1,100 kilograms. Then the acceleration of the car is the sum of the forces divided by the mass. And these are all this is in the x direction that we're looking at right now. Notice mass does not have a direction. So we wind up with 110 over 100 over 1,100, and this should be 1 over 10. So the accelerator is about 0.1 meters per second squared. Now, if they can keep that up for 10 seconds, they're going to be going 1 meter per second, right? Because the initial velocity is equal to 0. Final velocity when t equals 10 seconds would be final velocity is equal to 0 plus 0.1 times 10, which will be 1 meter per second. So we're still going to go back to these guys. All right. Oh, here's what they're saying. What if the mass of the car is 1,850 kilograms? All right, same thing, 0.059 meters per second squared. Okay, the direction of the force and the acceleration vectors can be taken into account by using x and y components. We'll do this a lot. In fact, you got some homework problems that look like that. I just wanted to get us started. So I'll look at one more problem, one more thing, and then probably one of your homework problems, and then we'll stop.